So at this point, we've covered concrete lifetimes for regular values. Let's now move on to discussing lifetimes for references. There's an important nuance to point out here. A reference is a value. It's a piece of data like any other. However, a reference represents a memory address of another value. So by its very definition, a reference is dependent on the existence of an original value. A reference cannot exist independently by itself. The concrete lifetime of a reference follows the same rules as the values we saw in the previous lessons. The lifetime of a reference starts when it is written to a location in memory, when that address is stored somewhere, and the lifetime of a reference ends when it is moved or dropped from that memory location. But there's one additional constraint when it comes to lifetimes for references. A reference, again, is intrinsically linked to a starter value, the one that it is borrowing. So it is critical that the reference does not outlive the original value, or the reference may then accidentally refer to invalid data. So thus, Rust will validate that the reference's lifetime is contained or lives within the lifetime of the referenced value. So this ensures that the reference points to a valid value for the complete existence of the reference. So remember, we mentioned earlier on in the course that a reference is like an address to a house. It is not the house itself, it is an address to get to the house. So in real-world terms, the Rust compiler is going to validate that the address of a house does not outlive the house itself. There is a lot of danger if a reference stores a memory address of a value somewhere else that is no longer valid or no longer exists. If you show up at an address and there is no house there, you'd be pretty frustrated in the real world. And similarly, in programming languages, when that happens, that can lead to serious bugs. So most of the time, when we're talking about lifetimes in Rust, usually we're going to be referring to the region of code that a reference can exist. So all values in Rust have a lifetime. That was the point I was trying to indicate in the two previous lessons. But the topic of lifetimes, it's usually referring to the lifetime of references because that's where the danger lies. That's where the capacity for error occurs, especially in other programming languages. The Rust compiler will ensure that all references have a valid lifetime that is completely within the lifetime of what is being borrowed. So if your program compiles, your code is fine and there are no errors within it. But sometimes getting to that point can be a little tricky. So you'll often hear the term borrow checker in the Rust community. The borrow checker is just a part of the compiler that checks that all borrows, i.e. all references, are valid. Once again, what does it mean for a reference to be valid? It means that the reference is pointing to some real data, existing data, present data. If the value that is being referenced moves to another memory location or is deallocated, the reference, which represents an address to that original value, all of a sudden becomes invalid. And that's what we have to watch out for. So that was a lot of technical jargon. Let me show you a concrete example to hopefully give you a little bit more clarity. So let's declare a dog variable, and I'm going to set it to a string of Watson. So as we know, the lifetime of dog and this string starts when it's declared and ends when the dog variable goes out of scope. That is the lifetime of the string itself. Below, I'm going to declare a myPet variable, and I will make this an immutable reference to dog above. So the value being borrowed from, in this case dog, is sometimes called the referent. The referent is what is being borrowed. The reference is the actual borrow. This is the memory address of dog that myPet is storing, but the referent is what is being borrowed. Okay, Sometimes it's also called the lender because it lends out or borrows out the value. Dog is the original piece of data, and it is being borrowed by my pet. Now, let's talk about the lifetime of the my pet variable. The my pet reference starts on line 3 when the reference is declared, and it's going to end similarly when we reach the end of the scope. The my pet variable goes out of scope, and then the reference and its life ends, right? The lifetime concludes at the end of the function scope. But the additional constraint here is that the lifetime of my pet must be contained completely within the lifetime of dog. Because if dog stops existing, then the reference to dog is also invalid. It's a reference to data that is no longer alive. If this dog dies, pardon the dark terminology, then the reference to the dog cannot be valid. So when you have a reference like this, the additional constraint that the borrow checker is checking for is that the lifetime of this reference must completely fit within or be contained within the reference lifetime. The borrow must exist completely within the lifetime of what is being borrowed. Of course, we can output these values below. And these are all valid examples because Rust knows, for example, that if we output my pet, it knows that it can track down the reference to the original value because it knows that the my pet reference lives within the lifetime of dog, and thus it knows it can track down the original value at the memory address that my pet is storing and get the text of the string, which is Watson. So here is a variation of the previous example. Let's drag my pet into a nested block. So right here, I'll create a nested block, and I'm going to move my pet into there as well as my output. So this is a slightly different example, but it serves to demonstrate the same point. The my pet references lifetime begins with this declaration right here with the ampersand, and the lifetime ends at the end of this nested scope. So roughly line 7 is when the reference is no longer alive. So my pet and its lifetime, the lifetime of the reference, concludes right here. Starts right here, ends right here. Why does the compiler and the borrow checker consider this valid? Because this reference lives entirely within, or its lifetime rather, lives entirely within the lifetime of the dog string. We can think of the dog string as being the region of code from here to here. This is the lifetime of dog, and as we can visually see, the lifetime of the my pet reference fits completely within that region or area of code. And so here's another example. I'm going to do a very similar thing. I'm going to copy and paste this nested block one more time below. So now we have two independent my pet variables declared in two separate independent nested scopes. And Rust is going to validate that the lifetime of each my pet reference lives within the lifetime of the referent or the lender, the original data that the reference is borrowing or referring to, pointing to. So in this situation, this code is once again totally fine because Rust has that validation. Rust sees the concrete lifetime of dog starting from here and ending at the end of main, and these two references, independent as they are, fit within that region. It fits within that lifetime. And we're going to continue to reinforce these concepts and practice with more examples throughout this section. But hopefully the basic gist of this stuff makes sense. All right, that's all there is to cover in this lesson, so I will see you in the next one.